Welcome back to this lecture on mathematical induction. In this second segment, we're going to study our first proof by mathematical induction. And here is the theorem we're going to prove. For all n in z plus, the sum of the first n positive integers is equal to the last integer in the sum times the next integer divided by 2. This is an equality that we've seen several times before, and we're finally going to be able to prove it here. So the first step is to identify the form of the theorem. For all n in z plus, p of n is true, where p of n is this expression. Let's record that. P of n states that this equality is true. Now remember that p is a predicate. In other words, it's a propositional function. This is not a proposition because n is a free variable. So what you need to do is to pick a specific value and plug it in for n, and then you get a proposition. So in particular, we could replace n by 1 to get p of 1. So what is p of 1? Well, it's the expression you obtain from this one by replacing every occurrence of n by 1, and therefore you get the sum for I equals 1 to 1 of I is equal to this fraction here. So that's p of 1. That is a proposition. It does not contain any free variable. Notice I is not a free variable here. It's well defined. It will take the value 1 and then stop. Notice I is not a free variable here either. It will take on the values 1, 2, 3 all the way up to n. It is completely well defined. N here is the only free variable, and n can range over the whole set of positive integers. So what is p of n plus 1? Well, p of n plus 1 is what you get from this expression by replacing every occurrence of n by the integer n plus 1. So you get the sum for I equals 1 to n plus 1 of I, which is equal to this complicated fraction here. So why did I write down p of n, p of 1, p of n plus 1? Because these are included in the premises of mathematical induction. Notice in the definition of mathematical induction as an inference rule, we use the variable k, and we say k is an arbitrary integer. Here we're just going to use the variable n and n plus 1 instead of k and k plus 1. It doesn't matter. These are dummy variables anyway. So now we are ready to start our proof by mathematical induction on n. You should probably write it up here before you start the basis step. Now what is the basis step? That's to prove that p of 1 is true. So now we actually have to prove that this is true. We don't know yet. The easiest way to do this is to compute the left-hand side on its own, get a value for that, compute the right-hand side on its own, get another value for that, and hopefully show that these two values are actually equal. So what is the sum for I equals 1 to 1 of I? Well, that's just 1. What is 1 times 1 plus 1 over 2? Well, that's 1 times 2 over 2, which is also equal to 1. So we just proved that this quantity here is equal to that one, and therefore we completed our proof for the basis step, namely that p of 1 is true. Now let's turn our attention to the second subproof in our proof by induction. That's called the inductive step. That's when we prove that p of n implies p of n plus 1 for an arbitrary positive integer n. Since this is a conditional, we're going to do a direct proof, which means we're going to assume the hypothesis of the conditional, which is p of n. Remember, this is called the inductive hypothesis. And it's true for an arbitrary positive integer n. Now, what we have to do is to prove that under this assumption, p of n plus 1 also holds, meaning that this equality is also true. So one way to do this is to start from one side of the equality, say the left-hand side, and to perform equational reasoning, that is to rewrite this expression a number of times until you get to this expression. So let's start with the left-hand side. Now what can we do? Well, the only thing we know is that we know the value of this expression here. And notice this sum is almost identical to this one. The only difference here is that we have an extra term at the end of the sum. We go up to n plus 1, whereas here you stop at n. So it's easy to rewrite this sum using that one, right? Let's do that. This is the sum for I equals 1 to n of I plus an extra term. So we don't need a summation term here. We just need n plus 1, which is the extra term that's added here. And now the good news is we can use the inductive hypothesis to replace this summation with this closed form formula. Let's do that right now. Now notice, this is the proof of a conditional, so it makes a lot of sense that we use this hypothesis at least once in the proof. Otherwise, you probably have a wrong proof by induction. So I'm going to require you to not only use the induction hypothesis, but you always justify that step when you use it. So this is the one required justification in a proof by induction. Now typically the remaining steps in the proof will not need to be justified because they use simple algebra. Now don't lose sight of your goal. Your goal is to get to this expression here. So starting from here, we need to first get to a single fraction. So we're going to multiply and divide the second term by 2. And then we can reduce this expression to a single fraction with a common denominator 2. And finally, we need to factor out the n plus 1, which conveniently enough appears both here and here. So what are we going to be left with when we're done factoring it out? We're going to have an n plus a 2. So we're going to get this fraction. And we're almost there. Notice n plus 2 can simply be rewritten as n plus 1 plus 1. And we just showed by equational reasoning that this sum is equal to that fraction. And that is exactly p of n plus 1. Therefore, we just completed the second subproof, the inductive step. And since we had completed the first subproof, p of 1, earlier, we have completed our proof by induction of this theorem.